Hello ladies and gentlemen, welcome to lesson 7.7, talking about solving right triangles. And in solving right triangles, we're basically taking a right triangle and finding all of the unknown side lengths and all the unknown angle measures, and that's the process of solving a right triangle. So we should be left with no unknowns. Well, we know how to use the Pythagorean theorem in special right triangles to solve for missing sides. We know how to use the triangle sum theorem to solve for missing angles. But what if we only know one angle? How can we find the other two? Well, that's where today's lesson comes in handy. We're using inverse trigonometric ratios. So let's say for here, we're trying to find the measure of angle A. Well, we know that we can take, I don't know, something like the tangent of angle A, and that should equal 9 over 12, right? A is our reference, 9 over 12. But how do we get angle A by itself? If we want to undo a tangent so we have A by itself, well, to do that, we'll do what's called the inverse tangent. The tangent and the inverse tangent cancel, just like multiplication and division cancel, or addition and subtraction, and we're just left with the measure of angle A by itself. And that equals the inverse tangent of 9 over 12. So this is where those parts of your calculator come in handy that you probably have never used before. Above the buttons that say sine, cosine, and tangent, you should see inverse sine, inverse cosine, and inverse tangent. And if we take the inverse tangent of 9 divided by 12, we end up with the measure of angle A equaling 36.8699 degrees. Now, you don't have to just use the inverse tangent. We could have taken the inverse sine. So using angle A as a reference, if we took the inverse sine of, well, that would be 9 over 15. It'll also give us the measure of angle A. And if we take the inverse sine of 9 over 15, that's 36.8699. Which is the same thing we had before. So here we could have used either one of those or also the cosine as well. You don't have to write out this whole spiel every time. All you need to say is that the inverse tangent of 9 over 12 is what you're looking for, or the inverse sine of 9 over 15 is what you're looking for. And this is a brief layout of the definition in general of inverse trigonometric ratios. So for the inverse tangent with regard to angle A, the inverse tangent of BC over AC will give you A, or the inverse sine of BC over AB, or the inverse cosine of AC over AB. You can use any inverse ratio and use that to solve for an angle. So regular trig ratios we use to find sides. Inverse trig ratios we use to solve for angles. So let's do several examples together to make sure we get the hang of this thing. So here we're not going to use angle A, we're going to use angle C actually. So we're going to use a calculator to approximate the measure of angle C to the nearest tenth. Well, with regard to angle C, I know the opposite and I know the adjacent. So I'm going to use the inverse tangent. So the inverse tangent of 20 over 15 will equal the measure of angle C. And then if I take the inverse tangent of 20 over 15, let me do that very quickly here. It should equal 53.1301, but it tells us to round to the nearest tenth, so that's 53.1. We cannot use sine or cosine here because we don't know the hypotenuse. If you wanted to find the hypotenuse, you could use your Pythagorean theorem, or note that this was a triple to get 25, and then use inverse sine or inverse cosine. But this is the quickest way to do it for this particular problem using the tangent. Let's continue on and do some more examples. So, if A and B are acute angles in two different right triangles, use a calculator to approximate the measure of angle A and of angle B to the nearest tenth of a degree. So if we know the sine of angle A is 0.87, then the inverse sine of 0.87 will equal angle A. So we take the inverse and we switch these two around. And if we take the inverse sine of 0.87, it's going to equal 60.5 to the nearest tenth. Likewise, if we want to solve for b, we take the inverse and switch our two items here. So the cosine, inverse cosine of 0.15 should give us the measure of angle b. And if we take the inverse cosine here, the measure of angle b is approximately 81.4 degrees. And remember, these are in two different triangles here. Let's try an example where we have to find or solve a right triangle. So we're going to round decimals to the nearest tenth. We're going to solve it, which means we're going to go for each side that's missing and each angle that's missing. So let's start with the angles. Well, here we actually don't have to use any inverse trigs to find an angle. We know this is 42 and this is 90. So the triangle sum theorem says this has to be 48. So they all add to 1/8. We will have to use some trig to find some of our missing sides, however. Let's use our original angle as our reference point. And let's say I want to find for CB. Well, if I use 42, I know that this is adjacent here, and that CB would be opposite. So opposite and adjacent, that's my TOA, so I'm using the tangent. So if I take the tangent of 42, that should equal my opposite, CB, over adjacent, which is 70. Now, since my variable is on the top, instead of cross-multiplying, I can use my shortcut, and I know that I'm just going to multiply these two terms together. And if I multiply 70 times the tangent of 42, rounding to the nearest tenth, this should be 63.0 or just 63. My opposite side is 63. Now, I could use sine or cosine to find my missing side, or more simply, I can use the Pythagorean theorem. 70 squared plus 63 squared should equal AB squared. And if I solve for and simplify and take the square root and all of that good stuff, I end up with approximately 94.2 for the length of B, and that's in feet. Let's do some more examples using inverse trig. Maybe let's try a real life one, then we'll do another solving a triangle. So let's say here we have a theater, and we're building what's called a rake stage. The stage is going to be 30 feet long from the front to the back, but we're measuring that as the actual stage top. So 30 feet front to the back. The total rise of 2 feet here. Our angle of elevation, or our rake, is 5 degrees or less. It's 5 degrees or less. It's generally preferred for the safety and comfort of the actors. Is this in the range suggested? Well, we want to see if this is indeed 5 degrees or less. So we have to solve for that missing piece. Well, if this is our reference angle, we know that this is our hypotenuse. Let me write that in a color you can actually see. And this 2 would be our opposite. So if we're using opposite and hypotenuse, that's the sine. So the inverse sine of 2 over 30 will give us the measure of our degree, which is x. So if I take the inverse sine of 2 over 30, I end up with the degree measure, let's say to the nearest tenth, is 3.8. So yes, this is in the desired range. So oftentimes trigonometry is used to find certain angles in architecture or in engineering when you're constructing something. If you're not just an architect, if you work in construction, if you're a contractor, these things can be very, very important. Let's do another solving a triangle example. Let's do one, though, that doesn't give you any angles to start with, so we have to use some trig. So let's do this one, number 3. Let's start with solving for sides, because that one should be pretty simple. We can use our Pythagorean theorem. We can say that 7 squared plus, let me name these here. We can say 7 squared plus BC squared should equal 23 squared. And let's round to the nearest tenth just to make things a bit simpler for us, so 23 squared. And if we end up combining like terms and reducing and whatnot, this is 49 BC squared, 23 squared, which is, bear with me here, 529. So subtracting 49 from both sides, and then taking the square root, we end up with approximately 21.9 for BC. So we have our sides done right away using the Pythagorean theorem. Solving for angles, since we only know one, we can't use the triangle sum theorem. We have to use some inverse trig. I'm going to choose the, I'm going to solve for angle A first. And I'm going to use the values that were given to me and were not rounded, so 7 and 23. So adjacent and hypotenuse. Well, if I'm using adjacent and hypotenuse, that's the cosine. So the inverse cosine of my adjacent over my hypotenuse should give me the measure of angle A here. So if I take the inverse cosine of 7 over 23, that's 72.3 to the nearest degree. And now I can use my triangle sum theorem to find my third one. You don't really need to use trig again. I can just take 180, subtract the 90, and subtract the 72.3, end up with 17.7 degrees. And now I've solved the triangle. I found every angle and every degree measure, and every side length. Let's do one more that involves having to use some inverse trig. So let's do number 2. Rid of this and some space here. Well, again, solving for sides should be pretty easy here. I already know 2 sides. I can use my Pythagorean theorem to find my third side, 11 squared plus 18 squared. Let me label this. Equals AC squared. And then 11 squared plus 18 squared, and take the square root, you know the drill from here. Should be about 21.1. That's the length of my hypotenuse. And I'm done with the sides. Now I need to move on to the angles. Well, let's start with the 2 numbers that are not rounded, 18 and 11. And let's say we're looking for, this time, angle C first. So I know that the measure of angle C, if I'm dealing with these 2 values, I have the opposite and I have the adjacent, so that's tangent, my TOA, opposite over adjacent. So I'm going to take the inverse tangent of 11 over 18, opposite over adjacent, and if I do that, the measure of angle C should end up equaling about 31.4 degrees. And then using your triangle sum theorem, this should be 58.6 degrees, so they all add to 180. So I hope this video, some of these examples can be helpful. Feel free to email me or drop in before school or after school if it's a Monday or Wednesday. And hopefully we can do well in this assessment coming up. Hopefully you all understood it.